So, good afternoon, everyone. My name is Hostache. I'm with the Centre de Recherche Publique Gabriel Lippmann in Luxembourg. I would like first to acknowledge my co-authors, Giovanni Corato, Marco Chini, Melissa Wood, Laura Giustarini, and Patrick Matgen. So, I would like to present today to you a new approach for improving flood model predictions based on the sequential assimilation of SAR-derived flood extent maps. So for years now, it's more or less accepted that floods represent one of the most important natural hazards in the world, and one tool for managing and predicting floods is represented by hydrologic and hydraulic models. The problem with the use of such model is that we need some evaluation data, and especially some data to set up these models. The main issue is that the traditional observations like gauge data are punctual, so they are not necessarily representative for the large areas, and these are also scarcely distributed, and they tend to be reduced in the future. And the last point is that ground observation are often difficult to do during floods. So we need for new observation techniques to help modeling. And a good candidate for this is satellite SAR images of floods. So as main characteristic of this kind of images, they have day, night, and all-weather acquisition capabilities. They offer synoptic views over large areas, and they are more and more readily available. Here you can see an example of the snapshot of a tool we are currently developing with the JPOD team at the Environment and at the ESA, European Space Agency. So in this graph, what is represented is a simulated water volume on the Earth's surface, and it's linked with SAR image acquisition during the whole Envisat life. So each yellow dot corresponds to an acquisition. So what you can see here, especially, is that there are many images that have been acquired during flood events. This data will be improved, and the number of data will increase in the near future with the launch and the upcoming Sentinel satellites with higher revisit time. So the research question of our study is how to efficiently combine SAR remote sensing information with models for improved predictions. So I'll first introduce the scientific context and the study area. There are currently many state-of-the-art methods for deriving flood extent from SAR images, but there is no probabilistic framework to estimate error on these observations, and these errors are necessary for assimilation purposes. For the sequential assimilation in models, I would like to mention two main families of filters. The first one is the ensemble Kalman filter, and the second one the particle filter. Another point that I would like to highlight is that on the past studies, only water surface elevation derived from SAR image were assimilated in models. The problem with this is that then the processing of images is not really straightforward and can be long. And this is an issue for near real-time applications. With respect to the filters, the ensemble Kalman filter is more dedicated for Gaussian error, and this will surely not be the case with flood extent extracted from SAR image. So for our specific needs here, we prefer the particle filter. So the study area is the Severn River that was already mentioned by Paul Bates previously. The study area is close to Tewkesbury. We used as a test case the 2000 flood event. For this specific event, we got two Envisat wide swath mode images acquired just after the flood peak, so during high waters. As evaluation and validation of our method, we will use in situ observed water surface elevation and discharge data. And in addition, and not least, we got a set of aerial photographs that have been taken during the flood event. So here is an example of one of the two images that have been acquired during this specific flood event. So as you can see, in this image, water appears are dark due to specular effect, so with a very low backscatter value. From this, we can see that there are two main populations on the image histogram. One with low value that correspond to open still water, and the rest corresponding to, let's say, dry pixels. From this, the method we developed has two steps. First, we estimate the probability distribution function of open water based on a gamma curve. And then we infer from this the distribution of the rest of the image by differentiating the histogram and the gamma distribution. From this point, using the bias theorem, we can deduce the probability for any pixel, the probability to be flooded, knowing its backscatter value that is presented here. So 1 meaning certainly flooded and 0 no flood at all. Here you can see an example, the result of the technique that will be called that we call the flood probability map. So for the assimilation technique, I will first present the modeling cascade we use in this study. So the first things that we use are the error interim that we perturbed in order to generate an ensemble of inputs. The hydrologic model that uses this input is based on the superflex model. It outputs discharge that is at its turn used as input of the hydraulic model that is actually the least floodplain subgrade model. And at this point, the modeling cascade outputs water surface elevation, flood extent, and flow velocities. And the objective is then to use the data assimilation technique to improve the forecast of this model. To explain quickly how the particle filter works, in this graph you have the ensemble. So each dotted line corresponds to one model realization, and the blue line corresponds to the ensemble mean. So we run the model till we get an image, and then we assimilate this image in the model in order to update the predictions by recomputing a weighted mean of the ensemble. I'll go into detail. To combine the SAR flood probability map with the model, we use the assumption that we can use the binomial likelihood PDF. I will go further from this. Here is represented schematically the flood probability map, so with values between 0 and 1. And here, the model results. So for one model, 1 meaning that the model predicts that this pixel is flooded, 0 that it's not flooded. So by screening pixel by pixel the two information, we compute local weights for each pixel of the model, of a given model. And so if the pixel is predicted as flooded, we simply use the probability to be flooded from the observation. If the model predicts a non-flooded pixel, then we use 1 minus the probability of this pixel to be flooded. And then we do it for every pixel of the image, and then we got a weight for any model and any pixel, and we have to compute a global weight to aggregate spatially weights in order to know the probability of one of the given model, one of the models. The problem here is that you can see it is based on the product assuming that all the data, all the pixels have independent information. But if one of the weights is close to 0, then probably the model will disappear during the assimilation process. This is called degeneracy. And then to solve this problem, what we did is that we masked out part of the pixel. Indeed, we select only the pixel for which the models are in most disagreement, meaning that 50% of the particles says that this pixel is flooded and 50 not. So from this, we aggregate the weight only on the selected pixel, and we got global weights for each model. So I'll go to the results. Here, you can see the simulated water surface elevation acceptance load, so in the middle of the study area. The red line corresponds to the observation, the green line corresponds to the open loop, so without assimilation, and then the blue line corresponds to the assimilation. So you cannot see here that much a difference, but it's more clearly visible in the error, where the error are reduced after, due to the assimilation, thanks to the assimilation. So we computed from this water surface elevation hydrographs the RMEC during this period. So it goes from 31 centimeters before assimilation to 28 centimeters after the assimilation of the first image, and it remains the same after the assimilation of the second image. Here you can see the same results, but this time for the discharge at Saxon's load. So here the improvement is a bit more clear. You can see the same information for the error, and then the Nash-Sutcliffe efficiency goes from 0.64 to 0.33 for the two assimilation steps. Let's now compare the results of the model to flood extent derived from the aerial photographs. So here you can see the open loop results. So they are clearly, especially upstream, overprediction by the model. After assimilating the first image, we can see that these overprediction are significantly reduced, and then even more reduced after the second assimilation steps. So to conclude, we developed here a method for near real-time assimilation of SAR-derived flood extents into a flood prediction model. What's nice, especially, is that it's a good way for taking advantage of growing flood satellite image collections. So these images are available, and we can use them to improve models. The main promising results are twofold. First, the approach significantly improved the predicted flood extents. So this is interesting, but these results was a bit expected since we assimilate flood extents. Then the second result is that the approach also improves prediction on discharge and water surface elevation. As a perspective, I would say that this is an example of how to use SAR images to improve models in near real time, but there are also nice perspectives for improving models via reanalysis, like, for example, calibration. So this study was funded through the Paparazzi project by the National Research Fund in Luxembourg. We'd like to thank Jeff Neal and Paul Bates from Bristol University and Fabrizio Fenicia from EAVAG for their help in setting up the modeling cascade. I thank you for your attention.